So now we've had 3 satellite missions to discover the more details about the cosmic dynamic of the Big Bang. The first of these was launched in November of 1989, the Cosmic Background Explorer satellite, COBE for short. And with that, we were able to show the radiation really came from the beginning of the universe, and to map and detect the variations in this, the small variations. They turned out on average to be about 1 part in 100,000. So, if you've ever seen a billiard ball, it's smooth, very smooth in your hand. It's smooth only to about 1 part in 10,000. So the universe is 10 times smoother than the smoothest thing we're used to. The random variations of the atmosphere or the water in this bottle are a little more than the variations that you see in your universe. So the universe is incredibly smooth at the beginning and expanding almost equally in all directions, but there are these tiny variations, and they tell us a lot about the universe. So after the COBE satellite, we had the microwave anisotropy probe, WMAP for short, which was launched in 2000. And COBE took data for 4 years, WMAP for 7 years. So it was recently shut off because in 2009, we launched the Planck mission in May of 2009, and it started taking data later in 2009 because it goes too far out. And what we've done is steadily improve the angular resolution and getting better each time, and the sensitivity. So we're getting more and better detailed maps of what the universe looked like very early at the beginning of its existence. So I have a little movie to show you some of the data that are coming from Planck. By March, we're hoping to actually publish the cosmological maps from Planck. So this talk is just a little early for that, but I can show you a little of the data. So here's the satellite. It's out at the Earth-Sun Lagrange point 2, which is where you go in a straight line away from the Earth and the Sun until the combined gravity of the Earth and the Sun causes it to orbit at the same rate that the Earth does. And then you can keep your solar cells and your antennas pointed back towards the Earth and the Sun, but you can take data from the sky. So here's a signal coming from the sky being accepted by the satellite. And as it rotates around and orbits around, you build up a map of the microwave sky. You can see the plane of the galaxy. Here's our own galaxy. Because we have 9 wavelengths, at the short wavelengths, the dust from our own galaxy shows up very well. So you can see the galaxy plane. The galactic center is in the center of the map, 90-degree rate of the spiral arm. There we saw an optical picture, and now the resolution is good. I'll go on. So this, let me go back. Okay, I think we're ready to start again. Take you back to the mood. If I can have it there. I'm going to show you a movie that was made in 1997. And it shows you what we knew then and what we guessed. And then I will show you the mapping we're doing, and I'll show you another movie that is what we know as of a year ago, a little over a year and a half ago. And as you'll see in my talk, we're actually making our own progress right now. So this movie from 1997 with a Hollywood hit is a movie about a researcher who's looking for signs of extraterrestrial life and discovers it and sees and gets a signal, and that signal is decoded as instructions on how to build a machine. And it turns out that machine is a device to allow a human to come and visit the aliens. So here is the picture. I'll turn the sound off, because I don't like the sound. Okay, you'll see a white spot on the horizon. This is the researcher getting ready to travel to see the aliens. So we're leaving the Earth, going by the moon. You'll see very conveniently for the movie, all the planets lined up. Now we're going by Mars, and through the asteroid belt. It's the moon of Jupiter. And there's Jupiter with a giant red spot. Only discovered about 100 years ago. It's a giant hurricane, but it shows in the movie as a hurricane. You see some other moons of Jupiter. And then through the rings of Saturn. And on out, and eventually you start seeing the Kuiper belt, which is some of the debris from the formation of the solar system, and the Oort cloud, where we think comets is. Those were pieces that were made at the beginning of the solar system, but never coalesced into planets and got swept down to greater distances, or were greater distances. Now we go by the nearest stars, and then through one of the early Hubble pictures. This area is called the Relics of Creation. It's a big gas and dust cloud, which is collapsing to form stars. But when it forms a star, the starlight blows the dust and gas away and helps compress in order to make more stars. So you can see these interesting pillars. So these we had data for. We had planetary probes, we went by the planets, we observed them from the Earth, and we had early Hubble pictures by 1997. So when we got to greater distances, you have to make up a model for what a galaxy looks like. It looks like a nice star galaxy. Then you get to go through a nearby galaxy. It's either Andromeda or Coronus. There's some miniature galaxies around us. And you'll see there's a lot of galaxies in the background. Here we get to go through another one. And we gain speed all the time. So all of this is made up, special effects. But there are very many galaxies out in the universe. And finding it up in a room where you get to meet the aliens. So if you don't recognize those blue eyes, that's Jodie Foster. It was in the movie Contact. Okay, now maybe I should get back to the talk in a second. But what I'm going to show you is that movie was based on our best guesses, and it's not so far from what we're seeing. But there are other really more interesting things we've learned about galaxies and stars, and about how the universe fits as a whole. And hopefully this will work. So we'll have to show you the other one. Okay, now we're resuming. And we'll quickly look at blank taking data again, I hope. So here's the satellite rotating out more than 1 billion kilometers further from the Earth than the Earth is from the Sun. And it's out there at around 22, taking data. We have over 2 years of data now. One of the instruments is no longer taking data because we run out of cryo. But while it was taking data, here's some of the real data it took. Absorbed the light coming from the sky and divided it up in the frequency band, and then rotated around many, many times and averaged things together in order to get our resolution map. In the center, we see mostly the dust from our galaxy because of the short wavelengths. But out of the edges, far away from the center, we see the signal from the galaxy itself. these kind of data, we have a brief history of the universe. If you consider the universe of the present day, there's a sphere around us, which is roughly 14 billion light years in radius. And from that sphere, inside that sphere, we can see many galaxies, because the light doesn't cover us. But if we take a slice of that sphere and trace its history backwards in time, we see it was smaller diameter further back. Now it has much smaller diameter, so this plot is not a linear plot. But what you'll see is, in more recent times, it's been getting bigger faster. That is, the rate of expansion has been increasing. We call that the period of accelerated expansion. And we assume that there's some mechanism causing that. And we give it the generic name dark energy. We don't know what this dark energy is. It could be some modified form of gravity, or we think most likely it's some new form of energy that's in the universe that we hadn't noticed before. It's only manifesting itself now in the later part of the universe. And as we go back, the universe was expanding at a slower and slower rate. And during this period is when the universe cooled down, the first stars and galaxies formed, and those then merged and developed to become the modern day galaxies we see. And also generated the planets. Our own solar system was generated roughly in this epoch, about 2/3 of the way through the current history of the universe, about 4.5 billion years ago. We can date it fairly accurately with radioisotopes to 4.55 billion years ago, when the Earth formed and the Sun and the other planets were forming almost at the time. The whole solar system formed in this kind of a year. As we go back further, there is some time period where there are no stars and galaxies because they haven't formed yet. We go back to the universe is about kind of smaller, and we have this region that we can detect, and we think we can trace things back even further. And as we trace it back even further, what hydrogen physics experiments give us information about. As we trace it back further and further, the universe that we can see around us gets smaller and smaller. So everything we can see, the region that has 100 billion galaxies, each on the orders of hundreds of billions of stars, goes in a region that was smaller than the size of an atom. And at that point, quantum mechanics is important. The uncertainty principle tells you there are going to be perturbations and variations. And you can easily calculate how many of those there should be per given size of the universe. So if you say there's only 1 or 2 across the whole horizon, by the time you get down to the size of galaxies, you get a number of perturbations that's on the order of 100 billion. That is, roughly every galaxy corresponds to a quantum fluctuation back into the time when the universe was macroscopically small. So we have this beautiful picture that we had everything packed together. We made it nearly perfectly, but quantum mechanics says you can't be perfect. There must be some fluctuations of uncertainty. And those fluctuations of uncertainty, they eventually become wonderful things like galaxies and clusters of galaxies, and even clusters of galaxies. So that's our picture. So how are we going to take that out? Well, we need the spheres around us. We need to take these slices at different times, different distances, and see if that corresponds to the model that we see. So let me tell you about the digital sky surveys that are being done. So the first one I'll show you pictures of is the Sloan Digital Sky Survey, which Sloan 1 and 2 have mapped the location of about 1 million galaxies. And so in this picture, you get a picture of this left side bubble picture. You can throw away the stars because they have this funny shape compared to what galaxies do. And then for each galaxy, you can find its angle on the sky, and you estimate its radial distance, and then you put a plot into a map. And every one of these dots in here is a galaxy. And if you could count them all, there's roughly 1 million of them